the James Webb Space Telescope is identifying objects in the dark ages that, by best measurements we have, are large, fully developed galaxies. So who ordered that?
For nearly all of the 20th century, the biggest question over the expanding universe had to do with understanding what its fate would be. The universe, if it's expanding, had to be a race between two seemingly irresistible factors: the initial expansion rate, which worked to drive everything existing within the fabric of space mutually apart, and the force of gravitation, which fights against the expansion and works to pull everything back together again. Ever since the 1920s and 1930s, when the expanding universe became well established both theoretically and observationally, the primary quest of cosmology was to measure the present expansion rate as well as how it changed over time. Those two pieces of information together would allow us to infer the ultimate fate of the universe. Even after the Big Bang became established as our universe's beginning, scientists worked to improve these measurements, endeavoring to learn whether our cosmic expansion would eventually reversian recollapse, whether it would coast and continue to expand forever, or whether it would be right on the border between those two cases. The critical observations at last came in during the 1990s, determining that the answer was none of these options. Instead, the universe's expansion is accelerating, implying that a novel form of energy, dark energy, has come to dominate our expansion. It also implies that the universe we can observe is disappearing from our reach, and most of it is already gone. This idea is strongly supported by the surprising data obtained from James Webb. For little more than 2 years in space, NASA's $10 billion proves it's worth every penny. Historically, our grandest views of deep space came from Hubble. But as of July 2022, James Webb takes us beyond what anything else has seen. From the faintest galaxies to the richest clusters, to mostly empty cosmic voids, to the deepest depths of far-off space, and much, much more, the superior telescope has revealed details we've never seen before. Beyond all expectations, when James Webb focused on large regions of space that appeared blank to Hubble's eyes, it detected something mind-boggling. 900 trillion stars have mysteriously vanished into the void of space, and things are getting scarier by the minute. What happened? Where did stars go? How did they utterly go without a trace? Join us as we dig deeper into the shocking discovery made by James Webb, how Webb reveals details we've never seen before, and how the disappearance of that many stars might affect our planet as well as our very future. First off, accept that. James Webb outperforms Hubble by more than we expected. And when you look at the capabilities of James Webb and Hubble side by side, you would expect that our newest space telescope could do much more in less time. Whereas Hubble has a primary mirror that's 2.4 meters across, Webb's segmented mirror spans 6.5 meters. This leads to a resolution that's 270% as sharp for the same wavelength light, and light gathering power that's 730% as great as Hubble's. From the physics of optics alone, that's how much better and faster James Webb should be than Hubble, not including the advantages James Webb also possesses in terms of cooling, wavelength coverage, and instrumentation. In other words, for the same amount of observing time, you'd expect that James Webb would collect 730% as much light as Hubble. But James Webb, as you can see in the comparison of its composite image of galaxy cluster SMACS 0723 with that of Hubble, is doing even better than that. Hubble time is divided up into orbits, as from its position in low Earth orbit, it completes a revolution around our planet every 96 minutes. A total of 6 orbits, 4 in optical wavelengths and 2 in infrared wavelengths, were used to make the Hubble composite. You'd expect, based on simple math, that 6 orbits multiplied by 96 minutes per orbit would equal 9.6 hours, or 576 minutes of Hubble time. But there's only a total of 3.4 hours, or 203 minutes, of Hubble data that's gone into these images. despite nearly 3 times as much of Hubble's time having been devoted to this target. For comparison, James Webb observed this target for 12.5 hours and got 12.5 hours worth of data. What's the difference? Location. Hubble, because it's in orbit around Earth, spends more than 50% of its time with the Earth and the Earth's atmosphere, in the way of its desired target, and can only acquire useful data when its target is in full, unobstructed view of the telescope. Meanwhile, James Webb is some 1.5 million kilometers away at the L2 Lagrange point. It always faces away from the sun, away from the Earth, and away from the moon. It never has to contend with these obstacles to pristine observing, and so its observations of targets are 100% time efficient, as opposed to less than 50% time efficient like Hubble was. This improved efficiency extends to all observations taken with James Webb and should enable faster, better science than Hubble could ever achieve. In other words, James Webb gave us the proof we needed. Not only can James Webb find the objects that appeared blank to Hubble's eyes, in many cases, it can resolve them and examine their properties, whereas Hubble could not even see them at all. This helps us achieve one of James Webb's main science goals: to teach us, in the goriest details possible, how the universe around us grew up and came to be the way it is today. For instance, nearby, Jupiter appears as never before. Its bands, rings, aurorae, and moons appear alongside background galaxies. James Webb viewed exoplanets directly with infrared imaging. Spectroscopically, transits detect absorbed light and transmitted light, revealing molecular presences. Star-forming nebulae display unprecedented details. From new young blue stars to gaseous features, James Webb showcases what Hubble cannot. Meanwhile, Webb's initial alignment image grew spectacularly. Now a 140-plus megapixel view, it expansively reveals far-flung galaxies. Just 1% of this view contains 100 identifiable objects. Massive, evolved, complex galactic shapes appear at all observed distances. Additionally, disk galaxy candidates surprisingly appeared at extremely early times. James Webb also viewed the most distant star ever, Earendel. But arguably, its greatest images are of individual galaxies. Webb's views reveal gas, dust, stars, and more. Central black hole containing cores shine in mid-infrared light. Star-forming gas bridges appear between interacting galaxies. From Hubble to James Webb's near-infrared eyes, to the eerie, unfamiliar mid-infrared views, the universe is coming into focus as never before under Webb's watchful eyes. But in a shocking observation, James Webb has detected trillions of stars disappearing without a trace. But how? Where did they go? The two leading theories about what happened are that either it's still there, still erupting its way through its death throes with less luminosity and perhaps obscured by dust, or it just up and collapsed into a black hole without going through a supernova stage. But in the worst-case scenario, the universe is just disappearing, and we're powerless to stop it. To understand the dilemma, a brief refresher is needed. At the start of the hot Big Bang, the universe was rapidly expanding and cooling, while individual clumps within it were also gravitating. Over time, the expansion rate slowed and the temperature dropped, leading to the formation of stable bound structures for the first time. After about a microsecond had elapsed, protons and neutrons formed. After another few minutes, the first stable atomic nuclei were forged. Hundreds of thousands of years later, neutral atoms came into existence. And after tens to hundreds of millions of years, the first stars and galaxies came into being, all while the expansion rate dropped and dropped. For the first several billion years of cosmic history, this appeared to be precisely what was going on. The universe began expanding, but the gravitational effects of matter and radiation worked to pull things back together, slowing the expansion rate down. Objects that were farther and farther away appeared to recede slower and slower as time went on, and the light emitted by once invisible objects, far beyond the cosmic horizon, finally caught up to us, the observer. More and more of the universe came into view. And then, about 6 billion years ago, the matter density dropped by such a significant amount that dark energy's effects began to become important, and everything changed. Prior to this moment, if you had put your finger down on any distant galaxy, you would have seen that it receded from us, getting farther and farther away as time went on. However, if you measured its recession speed from us, i.e., how much its light was redshifted by the expansion of the space between that galaxy and ourselves, you would have observed that to decrease with cosmic time. Even as it moved farther away from us, the expansion rate of the universe dropped by a more significant amount, ensuring that although it still appeared to recede, it was receding slower than it was previously. This allowed the light emitted from objects at even greater distances to catch up to us over time, bringing them into view. However, at an age of about 7.8 billion years, or about 6 billion years ago, all of that changed. Objects at all distances, greater than about 5 million light-years away, that is everything beyond the local group that's gravitationally bound to our own galaxy, began receding from us faster than they had been previously. Fewer and fewer new objects would now come into view as they began accelerating away from us. The objects that were beyond a certain critical distance would remain visible, but we'd only be able to see the light they emitted in the past, not the light they're emitting today. Additionally, we'd be unable to reach them, either by spacecraft or with a light signal, even if we sent it right now. Only the closest objects would remain both visible and reachable, creating 4 distinct regions to our observable universe. Based on their present distance from us today, 13.8 billion years after the Big Bang in the dark energy-dominated era, we can classify the 4 regions that describe the objects within our universe. First, observable and reachable. If an object, at present, is closer than about 18 billion light-years away, we can both see it and reach it. If we sent a signal to a galaxy within this distance, even today, it would be able to reach that galaxy. And if we embarked on a journey to reach that object, we could reach it even at sublight speeds. Second, observable, but not reachable. If an object is more than 18 billion light-years away, but closer than 46 billion light-years away, it's still observable by us, but only as it was in the past. It can see us as we were in the past, but we cannot reach it in any way, not by spacecraft and not with a light signal. We are only connected to these objects in the past. Third, observable, but only in the future. If an object is more than 46 billion light-years away, its light will not have reached us yet within the expanding universe. However, if that object is also closer than 61 billion light-years away, the light it emitted long ago is already on the way and will reach us at some point in the future. Although we can only see it as it was in the distant past, at some point it will become visible to us. And last, forever unobservable. And beyond a distance of 61 billion light-years, no object will ever be visible to us or reachable by us. This is profound and remains unappreciated by most. Even though 18 billion light-years is 39% of the way to the edge of the observable universe, a seemingly impressive and substantial number, we live in 3 spatial dimensions. 3. 9% of the way to the edge of the observable universe in one dimension represents only 6% of the volume of the presently observable universe. In other words, even though there may be between 6 trillion and 20 trillion galaxies contained within the observable universe, only about 6% of them, the closest 6%, are presently reachable by us. The remaining 94% can only be seen as they were in the past. There are almost certainly galaxies beyond the limits of our presently observable universe, as we have every indication that beyond that boundary simply lies more universe as we know it. But their light, hasn't yet reached us. Although 61 billion light-years isn't that much larger of a figure than 46 billion light-years, it encapsulates an extra 133% of the volume presently contained in the portion we can see right now. There are more than twice as many galaxies that have never been observed that will someday become visible to our instruments than are in the presently observable universe today. Even though the universe keeps on expanding, eventually, that light, although red-shifted severely, will catch up to us. However, it's important to remember that this picture provides a mere snapshot of our existence at present. In reality, the matter and radiation densities are continuing to drop, the dark energy density is remaining constant, and the expansion rate, measured in kilometer per second per megaparsec, isn't dropping to zero, but is asymptoting to a positive, finite value. It's this last part that's extremely important. In any expanding universe in the context of general relativity, there's a relationship between the rate of expansion, also called the Hubble parameter, at any moment in time, and the square root of the total energy density from all forms, including matter, radiation, and dark energy. Right now, the expansion rate is, depending on which set of measurements you believe is more correct, either 67 kilometers per second per megaparsec or 74 kilometers per second per megaparsec. This means, for every megaparsec, or about 3.26 million light-years, that an object is distant from us, we see it receding from us by either 67 kilometers per second or 74 kilometers per second, meaning that objects that are 10 megaparsecs away recede at 10 times that speed. Objects that are 100 megaparsecs away recede at 100 times that speed, and so on. However, because the expansion rate is dropping, but only to about 82% of its present value, that means in the future, the expansion rate will asymptote to either 55 kilometers per second per megaparsec or 60 kilometers per second per megaparsec, or somewhere in between if that's where the true figure lies. Because of the enduring presence of dark energy, that doesn't just mean that 94% of the galaxies within the observable universe have already disappeared to be beyond our reach. It means that the universe is in the process of disappearing beyond our reach, and that while 94% of them have already crossed that milestone, the other 6% of them, including every single galaxy that isn't a part of our local group, are already in the process of disappearing. There are about 2 sextillion stars clustered into those trillions of galaxies contained within the observable universe, but only 6% of them, or around 120 quintillion of them, are presently reachable today. With each new year that elapses, hundreds of millions of additional stars cross over that threshold, from being reachable to being unreachable, corresponding not to a handful of small galaxies, but rather to portions of perhaps hundreds of galaxies, both large and small varieties. On extremely long cosmic timescales, however, these changes can be tremendous. After another billion years has elapsed, or just bog 7% of the present age of the universe, the percentage of the observable universe that's still reachable will have dropped by another enormous step, from 6% to 5%. That means just 1 billion years from now, after the last total solar eclipse has occurred on Earth, but perhaps even before the sun heats up sufficiently to boil our oceans, we will only be able to reach 100 quintillion stars, having lost another 20 quintillion, between 300 billion and 1 trillion galaxies, having now lost 95% of the total galaxies in the universe, and the galaxies that are presently located within the 16.7 billion light-years from us, having lost every object presently between 16.7 billion and 18.0 billion light-years away. We can go a little bit farther if we dare. Another 5.2 billion years ahead after that, further 1 billion years. At that point, the Milky Way and Andromeda galaxies will have begun merging, and the Sun should be transitioning into a red giant, where it will swallow Mercury, Venus, and possibly the Earth as well. And at that point, we'll only be able to reach fewer than 2%, about 1.75%, of the stars and galaxies within our presently observable universe, corresponding to just 35 quintillion stars, and between 105–350 billion galaxies. In the meantime, what we presently call Laniakea, our local supercluster, will have already begun visibly dissociating into its component groups and clusters, being driven apart by dark energy. It isn't just the most remote galaxies that expand away from us, being driven to greater and greater distances by dark energy. It's every galaxy that isn't gravitationally bound in the same group or cluster as our own. After roughly 63 billion years have passed by, all 100,000 galaxies that compose what is known as Laniakea today will be the only galaxies that are reachable by someone living in the local group. There will be around 100 quadrillion stars inside these galaxies, but many mergers will have occurred, leaving the number of galaxies a much smaller number than are present within Laniakea today. Over the following few billion years, the large clusters within Laniakea, things like Norma, Centaurus, Hydra, and Fornax, will recede beyond the reachability limit. The Great Virgo cluster of galaxies, only 55 million light-years away at present, and consisting of over 1,000 member galaxies, will become unreachable just before we reach the 100 billion year milestone after the Big Bang. And what are presently the closest galaxy groups outside of the local group, objects like the M81 group, will be the last to become unreachable. Something that won't occur until more than 110 billion years from now, when the universe is nearly 10 times its present age. Nearly 100 years ago, we began collecting the first evidence for the expanding universe, and with it, the first evidence of our cosmic origins, the original notion of the Big Bang. Once we began seeing very far back in cosmic history, not just millions or hundreds of millions of years back in time, but several billion years, we began to investigate not only our cosmic origins, but our cosmic fate as well. And what we found, to the surprise of many, was that our universe couldn't, but rather was dominated by a mysterious form of energy that was driving all gravitationally unbound structures apart: dark energy. Dark energy doesn't just determine the fate of the universe, it also determines the distance and time scales on which galaxies, galaxy groups, and galaxy clusters would all fly apart from one another. Today, 13.8 billion years after the Big Bang, we can see up to 46 billion light-years away, but only 6% of the volume of our observable universe can be reached by us. As time continues to progress forward, the amount of the visible universe that we can see will continue to increase, but the galaxies within the portion of the universe that's reachable will continue to decrease as they all move farther and farther away from one another. At last, after another 112 billion years pass by, the final galaxies beyond our local group, representing the closest galaxies to our own local group today, will finally recede beyond the reachability limit, receding too fast for even light to catch up to it. No restriction on the amount of time that can pass, then all of these occurrences are simply inevitable. The only question is when. Which brings us to an important question. If you're going to trigger a nuclear fission reaction with the Big Rip scenario, where the subatomic particles at the heart of each atom's nucleus are ripped apart into their constituent components, how much time do we have for that explosion to propagate throughout space before the universe itself ends? For nuclear explosions, the propagation time can be devastatingly fast. The above high-speed photographic sequence shows one of the original test detonations of an early atomic bomb in the 1940s, and you can see that in mere milliseconds, the explosion has expanded to take up a volume that's larger than the size of a football field, over 100 meters across. It's a rapidly expanding explosion resulting from a tremendous release of energy, but it's still slow, less than 1% of the cosmic propagation limit set by the speed of light. Unfortunately, by the time atoms and atomic nuclei themselves get torn apart, we're only 10^19 seconds away from the end of the universe. Even if the released energy traveled outwards at the speed of light, it would only travel about a third of an angstrom through space before the universe came to an end. This comes as a disappointment to most people. Sure, it's fascinating to think about alternative fates to the mainstream for our universe, but that requires something exotic. That dark energy be something even more bizarre and mysterious than is commonly thought. While either the cosmological constant or the zero-point energy of the quantum vacuum can be folded into our current theories without adding anything novel, something that causes dark energy to strengthen over time would require some type of new field, particle, or interaction. However, once you're willing to invoke such an entity, a number of fascinating possibilities for the fate of the universe suddenly arise. They include the universe spontaneously transitioning to a lower energy state, looking very much like a repeat of the end of inflation that kicked off the hot Big Bang, the act of tearing space apart, resulting in a sort of reverse singularity, where space and time can either be reborn or can disappear into nothingness, or the universe actually undergoing a cyclic phenomenon, where a closed time-like loop ensures that the universe plays again on repeat, just as it did before, except with the quantum outcomes of various interactions being no more predetermined than they were in this iteration of the universe. The Big Rip is one possibility for how the universe could end, but if dark energy increases with time, we have to face the facts. At some point, we're going to have to deal with energies and temperatures that are high enough that we've never explored them. In those regimes, anything that's not ruled out remains possible. Simply put, the universe is disappearing, and we're absolutely powerless to stop it. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.